Hello everyone, welcome to this lecture 33 of the NPTEL course on Riemannian geometry. So our aim for the next couple of lectures is to understand how to find shortest paths between two given points on a manifold, and that I mean, how does the geodesic equation arise naturally when you study this problem, right. So to motivate what we need to do, let us go back to what we learn in multivariable calculus. So let us say I am given a function f on some subset of Rn and it is a real valued function. So the goal usually is to find in all these optimization problems is to find the local extrema, right. So you can either look at the local maximum, the local minimum and so on, right. And the idea is that suppose P is a local extrema, then you take any path capital gamma which passes through P, so gamma of 0 is P. Then if P is a local extrema, then we have the first derivative test which says that if you compute the derivative of f composed with gamma of s at s equals 0, then that would be 0, right, because otherwise if it is non-zero then you can move in so suppose you are at a local minima, if the derivative is non-zero then you can and it is positive, let us say, then you can move in the direction which is negative of the tangent direction of gamma to further reduce the value of f, right. So if f is a local minima then that would imply that the derivative has to be 0, okay. And in fact this, if you remember, is equivalent to the statement that the gradient of f at p is 0, okay. So the problem that we are really interested in is that we will be considering certain functionals on the set of all possible paths. So these are called the length functional, which I have already defined quite a while back, and there will be another slightly more convenient functional to use, namely the energy functional. So these are defined on some set of paths, okay. So now we are suddenly, from the comfort of finite dimensional calculus, we are suddenly in an infinite dimensional case, because the set of paths in general will not be a finite dimensional space, right. So now the main questions that one would like to address even before one can talk about the first derivative test is what should be the allowed set of paths in omega. So this set omega, what all paths should you allow in omega. So of course one should allow smooth paths to be in omega, but in order to do first derivative test and develop this whole theory, it is actually useful to slightly enlarge the class of paths that you are allowed, okay. So we will define in today's lecture this class of admissible paths, so that is slightly bigger than the class of smooth paths. And then once you know what omega you need in order to develop this theory, one should also have a notion for the set of paths in omega, right. So these are the set of paths in the space of all paths, right. So one should also have a notion for all the allowed paths in omega. So the point of today of this particular lecture is to just develop these definitions. So I will define exactly what kind of paths will we consider, and I will also define what are the paths in the space of all admissible paths, okay. So the point of this lecture is to address these two questions, and then in the next lecture we will actually develop the first derivative test for the length and the energy functional. Okay, so the first thing I want to define are what are called as admissible paths. Okay, so these are essentially piecewise smooth paths that we have already defined during in the course of our proof of the local Gauss-Bonnet. So let me quickly go over the definitions again. So let gamma be a continuous curve. We say that gamma is admissible if the following two conditions hold. Firstly, gamma is piecewise smooth, so I will usually denote it or abbreviate it as P dot S. So let me remind you of what piecewise smooth means. That means there exists a partition okay such that gamma restricted to ak minus 1 to ak, this is smooth. Okay. So this is what being piecewise smooth means. So throughout this course of lectures I am always going to consider partitions of this type. This is going to be my notation usually for a partition. I will denote the points in the partition by a naught, a1, etc. So that is going to be the standard notation that I am going to use. And the second condition we want gamma to satisfy is that gamma is regular. Okay. So what this means is for all the smooth points, which means t is not equal to k, either okay or it is never 0. Okay. So we allow this first condition so that we can also talk about constant paths, paths that do not move. Okay. It is convenient to allow to think of constant paths as also admissible paths. Alright, so now let us go back to this definition of piecewise smooth. The fact that gamma is smooth on this closed interval just means that there is a extension to an open interval containing this closed interval, right. So what that means is as a consequence of that, one thing to note is that the limit as t approaches ak minus of the derivative, so you have this interval and this point ak. So as you approach ak from the right or from the left, these limits exist, the limit of the velocity vector exists by definition of what it means for gamma restricted to a closed interval to be smooth. So we denote this usually by gamma dot ak minus, and similarly limit as t approaches ak from the right as gamma dot ak plus, and then the jump in the velocity vector is defined to be this. Okay. For k between 1 to m minus 1. Of course, this does not make sense at the end points, because for instance at the left end point there is no further point on the left, similarly on the right end point there is no further point on the right. So at the two end points one can only define a one sided limit. Okay. Alright, and notation is nomenclature is that gamma of A is called the initial point and gamma of B is called the end or the final point. Okay. Alright, so I also need to define what are called as admissible vector fields. So let gamma be an admissible curve as above, as in the definition, an admissible vector field along gamma is a continuous function x from the interval a to b, the interval on which gamma is defined, to the tangent bundle, such that the following two conditions hold. Firstly, x of t is a tangent vector at gamma of t, okay, and there exists a partition which I will denote by a naught tilde, a1 tilde up to am tilde, such that x restricted to this interval is smooth. Okay. All right, then a remark is that if gamma is admissible, the velocity vector is an admissible vector field if and only if it has no jumps in the velocity vector, if there are no jumps in the velocity vector. This is because by definition we require our admissible vector field to be continuous at least, right, and the velocity vector of a admissible curve may not be continuous, it may have jumps. So the notation that we will use is the following. So omega m will denote the set of all admissible paths omega p comma q is the set of all gamma in omega of m, such that the initial point of omega is p and the final point of the initial point of gamma is p and the final point of gamma is q. Okay, so these are the admissible curves going from p to q. So a picture could be something like this, right, because they are only piecewise smooth, right, and chi admissible on gamma is the set of admissible vector fields along gamma. Okay, so this is the notation that I will use throughout. All right, so now I come to the main sort of functionals that we want to optimize. So they are the so called length and energy functionals. So I will denote them by script L and script E. So they are functions on omega m to r, so the real valued functions on omega m, and the definition is the following. So L of gamma, so let gamma be as above. So that means we have this partition a naught, a1, etc., such that gamma restricted to these closed subintervals is smooth. So then you define the length of gamma to simply be the integral of the speed. Okay, so of course gamma need not be smooth throughout. So when I write such integrals, what I really mean is that this denotes the following sum. You calculate the distance travelled by gamma on each of these subintervals. Okay, so this is what I mean by that integral. Similarly, we define the energy functional which involves the square of the speed. Okay, and again what I really mean by this is this sum. Okay. Alright, so the reason to prefer the energy functional, so one prefers for two reasons. One is a sort of simplistic reason, that it is much easier to take derivatives of squares. Right. So in other words, it is much easier to compute things like d by ds of f square rather than d by ds of absolute value of f, right. Okay. The more important reason is that as we shall soon see, the length functional is invariant under reparametrizations. Okay, so whenever you are doing variational method, if you have a function that is invariant under a certain class of objects, then or invariant under certain operations, then that variational problem somehow becomes slightly trickier. Okay. So as we shall see in the next couple of lectures, when we talk about the first variation formula, it will be easier to understand the critical points of the energy functional rather than the length functional. For the length functional, because it is invariant under reparametrizations, one has to choose a certain normalization in order to study the variational problem, right. So we will get to that in the next couple of lectures, right. So this is the first remark. However, note the following, that by the Cauchy-Schwarz inequality, and I will leave this as an exercise for you to figure out, but I have already told you that this follows from the Cauchy-Schwarz. We actually get this this relation. Okay. So in fact, it will turn out that studying the variation of the energy functional will actually be good enough for all our applications because of this this inequality. Okay. So right, and with equality, if and only if the speed is a constant. Okay. So this is this is going to be useful in the future, right. So since I have talked about reparametrizations, let me formally define what a reparametrization is for admissible curves. Okay. So here is a definition. So let gamma from A to B to M and sigma from C to D to M are admissible curves. Okay. So we say that sigma is a reparametrization of gamma if there exists a homeomorphism phi from C comma D to A comma B such that the following holds: that there exists partitions, let us call it A equal to A naught less than A1 etc. up to AM, and C naught etc. up to Cm is the partition of C to D. So by choosing possibly refinements of these partitions, I can always assume that that the number of parts in the partition is the same in both the partitions, okay, such that gamma restricted to AK minus 1 and AK and sigma restricted to Ck minus 1 to Ck are smooth for all k, and phi from AK minus 1 to AK to this interval Ck minus 1 to Ck is a diffeo. So which means that it is smooth, and the inverse is also a smooth function as a function on closed intervals, okay. And of course it is called a reparametrization, so sigma of S better be gamma of phi of S, okay. So we say that this phi is orientation preserving or it preserves the directionality of gamma. We will abbreviate this as OP if phi prime is strictly positive. If phi prime is strictly negative, we call this orientation reversing, okay. Okay, so here is the key proposition that we will need. This is basically an exercise in multivariable calculus, which I am hopefully you have seen it before. If not, you can just quickly try to prove this proposition for yourself. So if sigma is a reparametrization of gamma, then as I was saying, the length functional is unchanged, okay. Also if gamma is such that gamma is non-constant and regular, so that means the speed never vanishes at any of the smooth points, then there exists a phi such that the reparametrization has unit speed, okay. So we say that sigma is an arc length parametrization. So rather we say that phi is an arc length parametrization of gamma, and sigma we call it a normalized curve or a normal curve, okay. Alright, so remark on the proof. So the first part I will leave the details as an exercise. For the first part we basically use chain rule and see that gamma dot of S is precisely sigma dot of S is precisely gamma dot of phi of S times absolute value of phi prime of S, right, and then you just use change of variables or the substitution law, okay. For 2, why is it called an arc length parametrization? You simply take you simply define S to be the arc length, so you define S of t to be the arc length from A to t, okay, and then take phi to be the inverse of this arc length function, right. So okay. All right. So you can try to fill in the details by yourselves. So now we have so far defined this omega, which is the set of all admissible paths, and we have defined our functionals that we are interested in on this omega. So the final thing in order to set up this variational problem is what should be the paths in omega. Okay. So that brings us to what are called as the admissible variations. Okay, so here's the definition. So let gamma be an admissible path. So let gamma be an admissible path, then an admissible variation of gamma is a continuous function capital gamma, which is defined on some interval containing 0 cross the same interval a to b to m, such that 1 gamma, when s is equal to 0, you should get back the original path that you began with. And the second point is that there exists a partition again let us denote this by a naught, a1 up to am, such that gamma restricted to the interval minus epsilon to epsilon cross ak minus 1 to ak is smooth. Okay. And the third point is for all s, if you denote by gamma s of t as capital gamma s comma t. So by the way, I will keep this s is the same as this s, right. I will keep sometimes I will write cursive and sometimes not. So in the future, if you should not be confused, these two are the same things. Okay. All right. So for all s in minus epsilon to epsilon, I want this to be a regular curve. Okay. So if you have a capital gamma satisfying all these conditions, it is called an admissible variation. Okay. So the way you should think of this is you should think of capital gamma itself as a curve in the space of all paths, okay, as s varies. So as your s varies, so the picture is this is your central curve, let us say gamma. As your s varies, you get all these other curves, right. So this is at some s1, this is at some s2, this is at s equals 0, right, and so on. So you should think of capital gamma as a set of as a curve in omega. Okay. And finally I need the following definition. I also need to have a definition for an admissible vector field along capital gamma. So, let gamma be an admissible variation. Okay. So, an admissible so there are a few 3 more definitions. So, an admissible vector field along capital gamma is a continuous function V now from minus epsilon to epsilon cross A to B to the tangent bundle such that V of s comma t is in the tangent space to M at gamma s comma t, and there exists a partition such that V restricted to minus epsilon to epsilon cross ak minus 1 to ak is smooth. Okay. So, that is an admissible vector field along a variation. We also need a definition for transverse curves. So, if you go back to the picture, we have these curves in gamma. So, the transverse curve is basically a curve that you get by fixing a t, right. So, you have all these curves in your variation. So, if you fix a t, you basically get another curve. So, that is what you call a transverse curve. So, you will usually denote this by t gamma upper t. So, this is simply gamma s comma t, and then we define the following. Del s of gamma at s comma t is precisely the velocity vector of these transverse curves. Similarly, del t of gamma is precisely the velocity vector of the horizontal curves. Okay, so that is going to be our notation. Then third, we call V of t, which is simply del s gamma at 0 comma t, the variation vector field. Of capital gamma, right. Okay, and finally, we say that gamma is proper if the endpoints are kept fixed. So, if for all s gamma s at A is the same as gamma at A, and gamma s at B is the same as gamma at B. So, the endpoints are kept fixed. Okay, so maybe let me end the lecture, this slightly longish lecture, because we are setting up all the notation. So, let me end with the following remarks. Firstly, the variation vector field V of t is actually an admissible vector field. That can be easily checked from the definition. The second point is that even if the horizontal curves are only piecewise smooth, the transverse curves are actually smooth for all t. Okay, even at the problem points t equals ak, if you think about what our definition for capital gamma is, these transverse curves are always going to be smooth. and hence if you look at V of s comma t as del s. So, the velocity vectors of the transverse curves, this is then always going to be continuous. And hence this gives you an example of an admissible vector field along capital gamma. Okay. All right. So, so let me maybe end with these three remarks. In the next lecture, we are actually going to talk about the first variation formula. So, let me maybe comment that this remark is slightly subtle. So, maybe in the next lecture, since we have already run out of time, in the next lecture I'll explain a little bit why this is always continuous. In S this is continuous because of this. Why is it continuous even in t, in the t variable, right? I'll maybe explain that a little bit next time, and we'll prove the first variation formula in the next lecture. Alright, so that's it for now. Thank you for your attention, and I'll see you in the next lecture.